Bismillahirrahmanirrahim. In the name of Allah, the most beneficent, most merciful. Dear students, I am Dr. Asrar Ahmad, and it's my lecture number 20 that is related with the Arrhenius equation, and this Arrhenius equation shows the effect of temperature on the rate of a reaction. This lecture belongs to the chapter Reaction Dynamics, and the course code is 4146. Dear students, the rate of a reaction depends upon the temperature. So in this topic, we will study that rate constant of a reaction that is a function of temperature and any other factor that affects the rate constant. So the rate of a reaction that depends upon temperature, we will see in this lecture that how they are quantitatively related with each other. It is a common thing that increase the temperature, rate of reaction will increase. Lower down the temperature, rate of reaction will decrease. But the question is that what is the quantitative relationship between temperature and rate of reaction? How much temperature we increase, how much the rate of reaction will increase. How much we decrease the temperature, and how much the rate of reaction will be slowed down. So, to answer this question, that what is relation, quantitative relation between temperature and rate of reaction, a Swedish scientist Arrhenius, he studied a quantitative relation between temperature and rate of reaction. And in 1903, he was awarded Nobel Prize for this valuable work. So, what happens when the temperature of a reaction mixture increases, then kinetic energy of the gaseous molecules also increases. So, due to high kinetic energy, there will be more effective collision, due to which the rate of a reaction will speed up. So, in 1903, a Swedish scientist Arrhenius, he studied a quantitative relationship between temperature and rate of reaction, due to which he was awarded Nobel Prize in 1903. Dear students, this is the famous Arrhenius equation, that is here in equation number 1, according to which the rate constant K is equal to A into exponential base raised to power minus EA over RT. K is equal to A into exponential base raised to power minus EA over RT. Dear students, in this equation number 1, the terms K, A, exponential base, EA, R, and T, these terminology mean that K is the rate constant. R is the general or universal gas constant. T is the absolute temperature, and EA is the activation energy. What is activation energy? It is very simple definition that the minimum amount of the kinetic energy in addition to the average kinetic energy of the molecules that is required to initiate a chemical reaction is defined as energy of activation, and it is represented with EA. So, EA means energy of activation. That means the minimum amount of the kinetic energy in addition to the average kinetic energy of the molecules that is required to initiate a chemical reaction. While A, this is called Arrhenius constant. This constant has been given this name to the scientist Arrhenius. Arrhenius constant means the rate constant of a reaction when the temperature approaches infinity. Arrhenius constant means the rate constant of a reaction when temperature approaches infinity, and it is the pre-exponential factor, or you can say it is the frequency factor, and this is associated with the orientation of the colliding molecules. And remember, the unit of the Arrhenius constant A, it will be the same as that of the chemical reaction constant, rate constant K. So the unit of the K rate constant and Arrhenius constant, they are the same. Dear students, now we will derive the Arrhenius equation, and we will study the quantitative relation between temperature and rate of reaction. So dear students, to understand, we suppose that we have a reactant A that collides with reactant B, and due to their effective collision, an intermediate product AB is produced. That intermediate product, according to collision theory, it will produce product B. So in the start, we have, suppose, A mole of the reactant A, B mole of the reactant B, and C mole of the intermediate product or transition state. So you can say collective A, B, and C, they are known as reaction coordinates. A, B, and C, they are collectively termed as reaction coordinates. Dear students, when reactant A and B, these two reactants, they react with each other, then a highly unstable activated complex A and B is produced. And this activated complex, when disintegrates, it is converted into product B. This activated complex is also known as transition state. So if you see this figure number 1, according to which if we take reaction coordinate along the x-axis and potential energy along the y-axis, then you can see when the reaction coordinates are increased. So here you can see the concentration of the reactant, it goes increasing like here, as you can see with the movement of this cursor. So this point is where the potential energy of the reactant is maximum, where A and B reactants, they have been connected through with each other, and here an activated complex has been produced. So yeah, you can see this point at which the potential energy of the reactant molecule is maximum. Here the activated complex has been produced, and with the increase in reaction coordinates, the potential energy of the system will decrease when this activated complex has been produced, and ultimately this activated complex will disintegrate into the formation of the products. So this figure is showing variation in the potential energy with the reaction coordinates. Dear students, remember that only those molecules will react, those have activation energy. Those molecules which have activation energy, they will produce activated complex. So quite often it happens that molecules which have energy less than activation energy also react to give products, but it happens quite often. But unusual phenomena is this, that this term will be called quantum mechanical tunneling. So quantum mechanical tunneling means if the unusual phenomena takes place, that the molecules which have energy less than activation energy and they give product, then we will say this phenomena is the quantum mechanical tunneling. But in general sense, you can say it mostly takes place only those reactants get converted into products which have high activation energy. So, if you see question number 1, it is in the exponential form. So, to understand that Arrhenius equation, according to which on the increasing temperature the rate constant will increase. So this phenomena can be shown in figure number 2. So in this figure number 2, you can see we have made a graph between temperature along x-axis and rate constant K along y-axis, and this is showing the variation of rate constant with temperature according to Arrhenius equation. So if the temperature is going increase, then the rate constant will increase. But at a point will come when this line will become parallel to this x-axis. So it means at a very high temperature, rate constant will not increase. So dear students, variation in the rate constant with temperature is dependent upon the value of activation energy. If the value of the activation energy is positive, then rate constant K will increase with temperature. If the value of the activation energy is positive, then rate constant K will increase with temperature, while for a negative value of activation energy, rate constant K will decrease with the increase in temperature. So the rate will increase or decrease. It depends that either the value of the energy of activation is positive or it is negative. Dear students, in case a high and positive value of activation energy, rate constant K is strongly dependent upon the temperature. Whereas for a low value of activation energy, it is weakly dependent upon temperature. So if we take natural logarithm on the both sides of the equation number 1, then we can say that this equation number 1 can be written as that log natural K is equal to log natural into a, that is the Arrhenius constant, into exponential base raised to power minus Ea over RT. So log natural K is equal to log natural A plus log natural into exponential base. They will be cancelled out. So their resultant will be equal to 1 according to rules of mathematics, raised to power minus Ea over RT. So by applying the mathematical rules, this equation can be written as that log natural A minus Ea over RT into log natural E. So since log natural E is equal to 1, so you can say that log natural K is equal to log natural A minus Ea over RT. Dear students, log natural K is equal to minus Ea over RT plus log natural A. So this equation number 2 is the linear form of the Arrhenius equation. Dear students, if we find the results of this equation, then we can say that this is the equation of straight line. And in the intercept form, where log natural K is the dependent variable and 1 over T is the independent variable. And if we plot a graph between log natural k versus 1 over t, we will get a straight line. And if you see this figure number 3, according to which along x-axis we have taken 1 over T, that is the reciprocal of temperature. While along y-axis, we have taken log natural K, and if we plot a graph between this log natural K and 1 over T, then we will get a straight line like this one. And the slope of this line will be equal to minus EA over R. EA is the energy of activation, R is the universal gas constant, and this minus means that this value will be decreasing with the time. So this figure is showing, figure number 3, the plot of the log natural K versus 1 over T according to linear form of the Arrhenius equation. Dear students, according to this figure number 3, the slope will be equal to minus EA over R, and EA, that is energy of activation, will be equal to minus slope into R. So intercept will be equal to log natural A. So Arrhenius constant will be equal to exponential base raised to power intercept. Dear students, from this relation we can find out the value of the Arrhenius constant by taking the intercept as a power of the exponential base. Dear students, we suppose that if we have a temperature T1, then rate constant for this reaction is K1. So if we write this equation number 2 with reference to temperature T1, we can write this equation number 2 that log natural K1 is equal to minus EA over RT1, because when temperature is T1, then rate constant is K1. So log natural K1 is equal to minus EA over RT1 plus log natural. Similarly, if the temperature is T2, then rate constant will be K2. So this equation number 2 can be written as log natural K2 is equal to minus EA over R T2, because when temperature is T2, then rate constant will be K2. So log natural K2 is equal to minus EA over RT2 plus log natural A. So according to equation number 4, we can find out log natural K2, and according to equation number 3, we can find out log natural K1. Dear students, now subtract the equation number 3 from equation number 4. So when you will subtract the equation number 3 from equation number 4, we will get log natural K2 minus log natural K1 is equal to minus EA over RT2 plus EA over RT1. So if we apply the rules of logarithm, we can write this equation that log natural K2 over K1 is equal to EA over R into 1 over T1 minus 1 over T2. And if we take the LCM inside this bracket, then we can write this equation in the form of equation number 5, that log natural K2 over K1 is equal to EA over R into T2 minus T1 divided by T1 T2. Dear students, this equation number 5 is an other form of the Arrhenius equation. And you can apply this Arrhenius equation at two different temperatures. At temperature T1, there will be rate constant K1, and at temperature T2, there will be rate constant K2. So you can find out log natural K2 over K1 by using this equation number 5. Dear students, this equation is very useful for calculating the value of activation energy of a reaction when the value of the rate constant at different temperature is known. And if you compare with the graphical method of finding the activation energy by using equation number 2, then we can say to study the kinetics of a reaction, at least 4 are different temperature, this equation can be implied. How? By just differentiating equation number 2. Dear students, if you want to study the kinetics of a reaction at 4 or 5 different temperature values, then it can also be applied by using the Arrhenius equation. How it is possible? For this purpose, we will differentiate equation number 2. If you differentiate equation number 2, that is log natural K is equal to minus EA over RT plus log natural A with respect to temperature, then this equation can be written as D log natural K over dt is equal to D into minus EA over RT plus log natural A over dt. This is the differential form of this equation number 2. This is equation number 2 and this is its differential form. Dear students, if you solve it further mathematically by using rules of differentiation, then this equation can be written as in the form of the following, that d log natural k over dt is equal to minus ea over r into dt raised to power minus 1 over dt plus 0. And according to rules of differentiation, we can write this right hand side of equation as EA over R into minus 1 into T raised to power minus 1 into minus 1, because here temperature is increasing from this state of minus 1, because this temperature was in the here in the denominator, so here it is in the minus 1 in the numerator. So by applying different rules of differentiation, we will get the equation number 6, and according to equation number 6, d log natural k over dt is equal to ea over rt square. So dear students, this equation number 6, that is the d log natural k over dt is equal to ea over rt square. This can be written in this form because equation number 6 is the differential form of the Arrhenius equation, and it can be used for the determination of activation energy. So if you calculate activation energy EA, it will be equal to R T square D log natural K over dt. This equation has been obtained from this equation number 6, just multiplying this RT square on both sides. Here it will be cancelled and here it will be multiplied. So energy of activation is equal to R T square D log natural K over dt. And dear students, this equation number 2, that is here, differentiating with respect to 1 over t, we will get like this one, d log natural k into d 1 by t is equal to d into minus ea over rt plus log natural a divided by d into 1 by t. So if you solve this right hand side, so this outside value will be multiplied with the inside value. So multiply this d over d1 by t with both these terms, so they can be written as ea minus ea over r into d over d1 by t into 1 by t plus d over d1 by t log natural a. So they have been multiplied with the inside. And after simplification, you will see by applying different differentiation rules that this term will be equal to 0 and here you will get 1. So d log natural k over d1 by t will be equal to minus ea over r So you can write this equation number 7, according to which energy of activation is equal to minus R d log natural K over d into 1 by t. So dear students, according to equation number 7, this d log natural K over d1 by t is the slope of the plot of log natural K, and it has been obtained by taking it versus against 1 by t, and R is the universal or general gas constant. So determining the slope and putting this value in equation number 7, it will enable us to calculate the value of energy of activation. So dear students, if a reaction, if for a reaction, the plot for log natural K versus 1 over T does not give a straight line, then it means the reaction will be showing non-Arrhenius behavior. So to know whether a reaction is showing Arrhenius behavior, is it following Arrhenius equation or not. So you just can check it for a reaction if the plot of log natural K versus reciprocal of temperature does not give a straight line. It means it is showing non-Arrhenius behavior. But if you make a graph and graph between log natural K versus 1 over T, and it is showing a straight line, it means that the reaction is showing Arrhenius behavior. So from the graph you can have an idea that whether the reaction is showing quantitative relationship between temperature and rate constant. Thank you very much. Take care of yourself. Allah Hafiz.